Okay, so it's December 21st, 2022. Last week, last week we had this really big news announcement from the United States Department of Energy proclaiming that it had achieved this elusive phenomenon in the world of nuclear fusion that's known as ignition. So, ignition is nothing more than a nuclear fusion reaction that yields more energy from the nuclear reaction than what was actually put into the materials in order to get them to the fusion conditions. So the big problem with nuclear fusion is that the conditions required to get atomic nuclei to merge together are very extreme. So here on Earth, in order to achieve fusion of nuclear fusion, the easiest fuel that we know of is what's called deuterium and tritium, or DT. Deuterium and tritium are two isotopes of hydrogen, a proton and two neutrons, or a proton and a neutron, a proton and two neutrons in the case of tritium. So basically those two things, you can heat them up to about 100 million degrees Celsius, and they will merge together and release a bunch of energy. Okay, the amount of energy released is very significant. It's actually more energetic of a reaction than on a per nuclei basis than what you get out of uranium, fission, splitting atoms, which is what we do at traditional nuclear power plants. So your traditional nuclear power plant is breaking large atoms apart. Uranium has an atomic number of 92. It's really big, and you split that apart. And all it takes to do that, it's actually pretty easy, is a neutron hitting that uranium nucleus, and that causes it to go unstable, and it busts apart, and it throws off more neutrons. And if you have enough uranium packed into a specific volume, those neutrons will then go hit more uranium atoms, who will then emit more neutrons, and you have a chain reaction, a self-sustaining fission reaction. You effectively have a fire, sort of, that uses nuclear energy. And with fusion, what was done at Department of Energy at the National Ignition Facility at Lawrence Livermore in California was kind of the fusion equivalent of that. And I just kind of looked at all these news releases, and this stuff was everywhere. Everybody from CNN, Fox, ABC, international news, Twitter, all these social media sites were, oh my God, fusion, the world's going to be bounty cornucopia of energy from fusion. And I just look at this like, okay, so why am I being skeptical of this whole deal? Okay, I really, anytime the subject of fusion comes up, which it always comes up in all these discussions about energy, people use fusion as this sort of, it's got a sort of, ceremonial kind of place in the whole world of energy discussions. And I've got to get this cat before she destroys our camera here. Come here. Hey. She'll jump up onto the chair and knock the camera off up there. So fusion sort of occupies this space of people, when we talk about renewable energy, like solar energy, wind energy, geothermal, hydropower, there's this sort of, why are we even worrying about that? Wow, when we get fusion, we don't have to worry about any of that stuff. And then you got the other side of it where I think fusion is used as a sort of like kick the can down the road, kind of deal, like, oh, well, global warming isn't going to be a problem once we have fusion. Okay, so people who say that, I don't know if they really understand the fact that this is, to use nuclear fusion as an electricity generating or an energy producing technology, on a commercial basis is extremely, very, very, very hard. It is probably, it's very, very difficult. And the incident of ignition that took place at the National Ignition Facility seems to really create a lot of optimism about fusion. And that's great. It's great to have that. And there's a lot of very, very, well intelligent and well-meaning people who are working at the National Ignition Facility. But at the end of the day, how is what took place at the National Ignition Facility any different than setting off a thermonuclear bomb? Okay? The news releases made it sound like we've never done fusion before. We've never done this. This experiment proves that we can do fusion, and it gives us hope for the future. That, obviously when somebody thinks that none of the energy sources we have now are any good, we got to wait till we have fusion, and all the world's problems will be gone. So, nuclear fusion is the same exact thing that's used in the thermonuclear hydrogen bomb. So here's basically what happened. So at the National Ignition Facility, they've got a laboratory with 192 lasers in it, big laser beams. Very, very powerful ones, megawatts, gigawatts, petawatts, whatever they are. They all fire a laser beam through and a bunch of optics. And the laser goes into this, chamber. And inside the chamber, there's this little tiny metal cylinder called a holram. The holram has inside of it a pea-sized blob of deuterium and tritium ice. So the deuterium tritium ice is in there, and somebody pushes the magic button, and all 192 lasers fire at once, and this radiation from these lasers hits this holram all at the same time, and within milliseconds or nanoseconds or something in that range of time, the entire little tiny pea-sized blob of deuterium and tritium is at 100 million degrees Celsius, at which point the nuclei are above the Coulomb barrier and they're able to merge together and form helium and energy and throw out a bunch of neutrons and radiation and X-rays and all kinds of very energetic stuff. And what they achieved at that time during that experiment was the pulse of laser radiation that went into the fuel was about 2 megajoules of energy. So about 2/3 of a kilowatt hour, a little less than half. A little more than half a kilowatt hour. So a kilowatt hour is 3.6 megajoules of energy. So if you visualize using a 100-watt incandescent light bulb for 10 hours, that's a kilowatt hour. There are 36 kilowatt hours of energy in a gallon of gasoline. 32, 36, something like that. And this reaction required about, a little over half a kilowatt hour went into the fuel, and about a little under a kilowatt hour came out. So 2 megajoules goes in, 3 megajoules comes out. You had a surplus of 1 megajoule of energy from this experiment. The laser supplied 2, fusion gave you 3, you've got an ignition, you got a surplus yield, a term borrowed from the nuclear weapons world, of 1 megajoule. Right? So, how is that any different than if I take a bunch of uranium or plutonium and I build a Hiroshima or Nagasaki kind of atomic weapon, and an atomic bomb, a fission bomb, and right next to it, in the proper configuration, I install a deuterium and tritium core for a fusion stage. That is what we call a thermonuclear weapon, a hydrogen bomb. We set off the fission stage, using the same technology they used in 1945 in the Manhattan Project. And the immense radiation and energy from that fission reaction goes over to our fusion stage and does the exact same thing to the tritium and deuterium that the lasers did to it at the National Ignition Facility. But instead of having a pea-sized milligram volume of fuel, we have, maybe a couple kilograms. I don't know how much they actually use, but some larger, much larger, orders of magnitude larger amount of fuel. Now suddenly we're yielding megatons of TNT from fusion. So, National Ignition Facility used 2 megajoules of laser pulse to make 3 megajoules of energy from fusion. Typical hydrogen bomb might use 5 megatons of energy from fission, and it will yield 5 megatons of energy from fusion, and you'll get a total yield of 10 megatons. Or maybe they'll yield 3 megatons from fission and 7 megatons from fusion, and you'll get your 10 megatons. Or in the case of the Tsar Bomba weapon that was dropped by the Soviet Union in the test, the largest nuclear weapon known to be detonated so far, 50 megatons of TNT equivalent, with the capability to go up to 100. And I remember reading that weapon had a fusion yield of like 97%. So 97% of the energy came from the fusion stage. Only 3% came from the fission stage, which is far better than what they achieved at National Ignition Facility using the lasers. So the idea that this is the first time is definitely not true. It's the first time that it was done in a non-nuclear weapon sort of configuration, but definitely not the first time that ignition has been achieved on Earth. So that really makes it into some interesting ideas here. If you look into the history of the National Ignition Facility, it was effectively funded through defense. And when the Department of Energy came out with its press release last week, they were very careful to make sure to say that this project contributes to national defense and future possibilities for energy systems, energy production, power generation, whatever it is. Because at the end of the day, what they are doing is just laboratory scale nuclear testing. It is a laboratory that is designed to simulate hydrogen bombs. It isn't designed to generate electricity. All right. Now, you can tell that I'm obviously not as excited about fusion as others were last week, because I just know the extreme difficulties associated with trying to do it. And if you look at what's going on at the ITER site, ITER, International Thermonuclear Experimental Reactor in France, you'll see how crazy, enormously complex and expensive fusion gets to be when you try to make it into something that can be controlled and operated as a power production technology. So at ITER, they are using what's called magnetic confinement fusion. Magnetic confinement is basically using a magnetic field to keep a plasma away from the walls of the reactor vessel. Because if that 100 million degrees Celsius plasma touches the walls of the vessel, it will erode the vessel and effectively ruin it, because it's very, very hot, very, very high energy. Those ions and atoms and things that are in there will strike that and knock material right off the walls. So they use magnetic field because plasma conducts electricity. It makes its own magnetic field, and they can basically contain the plasma in a sort of its own little, magnetic vessel. So that is the technology that is most likely to be used for generating electricity. But obviously, with inertial confinement fusion, there is definitely theoretical possibilities to use that technology to generate power. So we're setting off our little tiny pea-sized hydrogen bomb. In order to use it to generate power, we can't just set off one every 6 hours, which is what they could do at National Ignition Facility. That's the maximum rate that they can achieve. But they have to set them off like multiple, many per second or per minute in order to get enough power output to basically drive a commercial size megawatt, gigawatt scale power plant. Basically, you're setting off enough of these little tiny pea-sized fusion bombs emitting neutrons, and you're generating steam by capturing the neutrons in an absorber blanket that surrounds the vessel where the reaction is happening. And you're using steam to drive a good old-fashioned steam turbine, generate electricity that way. So if you look back to the 1960s, and you'll find that in the Plowshares program, there was a project proposal called PACER. And the whole idea behind PACER was to basically take what I just said, basically, instead of using a pea-sized hydrogen bomb, take it up to a full-scale megaton hydrogen bomb, or maybe kiloton hydrogen bomb, and out wet in the western United States, excavate a cavern underground, deep underground, and drop on an hourly basis a nuclear warhead in there and allow it to explode, and all of that energy will be captured in the rock as heat, and you can then capture that heat and generate electricity using thermodynamics through using a steam turbine. So that was a real idea that people actually thought up, using actual nuclear weapons as fuel for a power plant. And National Ignition Facility is nothing more than a miniaturization of that. Inertial confinement fusion is nothing more than a miniaturization of that idea. It's much more practical when you make it smaller and more manageable. And instead of using dirty radioactive fission reactions to ignite the fusion, you're going to use lasers. It's a little cleaner. You don't get all those radionuclides from the fission that are your fallout. That's the big hazard with fission weapons, is just the radioactivity. All right, so that's the idea. Now, let's think about the whole concept of, did they actually achieve net energy in terms of energy that was put into the National Ignition Facility, or energy that was simply put into the pellet of fuel? And the answer is the latter. So we had 2 megajoules that went into the pellet in the form of lasers. 3 megajoules of fusion happened. Now those lasers that they have, which are obviously laboratory equipment, they're not engineered for efficiency in terms of commercial power generation. Basically, they buy electricity off the grid. Pacific Gas and Electric sells them power. Whoever their utility is out there, they run it through their transformers. They bring it into the site. They bring it into the building. They put it through power supplies. They send it to probably flash lamps, and pulse the laser, pump the laser, frequency using optical stuff that I'm not even going to begin to think I know about, and send it into the fusion fuel. And that process from power to laser at the fusion fuel is about 1% efficient. So your 2 megajoules was actually 200 megajoules, or was it 0.5% efficient? I think it was 0.5% efficient. I remember hearing that it was 400 megajoules of electricity was needed to give you your 2 megajoules of laser. 400 megajoules of electricity, which is almost that's over 100. That's over 100 kilowatt hours. It's a lot of juice into your fusion fuel to give you 3 megajoules of what's effectively neutrons. And those neutrons in a commercial power plant would have to be captured, and that kinetic energy of those neutrons zinging away from the fusion has to be turned into heat. And then the heat makes water boil, which then goes to your turbine and generates electricity. You get about 33 to 35% efficiency with your typical standard issue steam turbine. Now, theoretically, you could probably get up to 45% efficiency, but that requires a lot more engineering on the power generation side of things. State of the art with coal-fired power plants is about 45% efficiency over in Europe, where they have higher energy prices and they can afford all the really good engineering of the plants. But I would expect a fusion power plant to be more on the order of 33 to 35% conversion of energy from the reactor to electrical power going out to the grid. Now, every power plant that's existing now, coal-fired, gas-fired, nuclear, they have all the internal systems at that plant that are powered off of the power plant itself. So you've got your main feed water pumps, you've got induced draft fans, forced draft fans, ball mills for coal, natural gas compressors, if not, all these different systems, even everything from the lights in the bathroom at the power plant run off of the plant itself. And I think that the standard issue number for a typical coal-fired power plant is about 10% of the electricity that they generate goes back into the plant to run all of the auxiliary systems. So if it's a 500 megawatt plant, they might use 50 megawatts to run everything at the plant. A big consumer of energy there is the main feed water pumps to pressurize the water going into the boiler. That's the big consumer of work on the Rankine cycle, generating power with steam. But in a fusion system, you have another major draw on the output, and that is the heating of the plasma, either using lasers like they did at the ignition facility, or in the case of a plant like ITER, over the magnetic confinement, you're using radio frequency, effectively microwave power, to ionize, to excite the plasma and keep it at the 100 million degrees Celsius range, especially on startup and things like that. So I believe that the fusion reaction itself should ultimately, whenever we get this all figured out, will keep the plasma hot. That's the whole goal. Sort of like, the fire keeps itself lit. As long as you keep adding fuel and you keep adding oxygen, the fire keeps burning. Assuming the fuel has enough energy value to do that. But you do have to supply power to cryogenic cooling for the magnets to confine the fusion. And, with inertial confinement fusion, you don't have the magnets and you don't have the cryogenics. But you have the lasers, which you can't bypass. So because it's intermittent, you always have to use the lasers. You can never rely upon the fusion to sustain itself once it's going, because it's intermittent. It's fusion off, fusion off, fusion off, fusion off, fusion nothing, fusion something. On and off pulses of energy. Whereas in a magnetic confinement, it's continuous. So the situation is that ultimately for these plants to work, they have to generate power for all their auxiliary systems, including heating of the plasma or containment of the plasma, or both. So that's sort of the long story of it. The way that I viewed this news release from Department of Energy and the National Ignition Facility was, we've succeeded at scaling down the hydrogen bomb to a pea-sized diameter. Okay, it is now possible for us to continue research into nuclear weapons using a laboratory that is capable of testing them on that type of scale. So we can actually visualize and put instrumentation in that reactor vessel and look at that fusion and see how it works and then scale that up to megatons. So that is probably what's going to happen much before we see practical applications for generation of electricity. In the meantime, I'm betting my energy on solar energy, wind energy, geothermal energy, and of course, nuclear fission is always an option too. Nuclear fission works. It's very expensive, but it works. It's commercially available. So that's the story of fusion. Definitely no panacea. And we have there's a lot of misconceptions about the radioactivity generated by nuclear energy. So you have fission, which famously generates this radioactive, waste material. And a lot of people think that radioactive waste, it's this green stuff in barrels, when in reality it's a solid, and it's really not that big in volume, but it is a challenge to manage. But that still exists in a certain form with fusion. So whether you're using inertial confinement or magnetic confinement, you're generating neutrons that when they fly out of that fuel and they zoom off to hit the walls of the reactor vessel, they will actually activate elements that are in that reactor vessel and make them radioactive, because the energy of those neutrons are such that will just happen. You don't have the shielding that you do in a fission reactor. Fission reactor, the core, the radioactive core, is actually shielded by water, and the vessel is hit with neutrons, but not as bad as it is in fusion. Fusion, the vessel's under vacuum. There's nothing to stop the neutrons. The neutrons are higher energy than they are in fission, and they slam into the walls, and suddenly now, to do all maintenance in your fusion reactor, you've got to use robots. And that's what's going on at ITER in France, is they're trying to come up with robotic maintenance technology to be able to do all the maintenance inside of that vessel, because once they light the deuterium, tritium plasma, people can no longer go in there and do work because it's too radioactive. So fusion, while different than fission, still produces radioactive materials. And they present different maintenance and management challenges, but they're still there. So that's the challenge with fusion. Right now, it's just a very, very far off possibility. And the engineering associated with it is beyond anything. I think we have a better chance of seeing a person end up on Mars than commercial fusion. Okay? Commercial fusion, a person ending up on Mars in some kind of, space mission before we see commercial fusion. Commercial fusion is obviously not impossible, but it's very, 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 very hard, as I've been saying this entire time. And that's it. That's my take on the fusion announcement from the National Ignition Facility.